DARPA, and some commercial projects with folks like BP, BASF, BMW, and excited to continue that.
Hi, Sierra Shakir. So I wear a few hats in quantum. I am the Director of Strategic Content at the Quantum Insider. So if you haven't heard of us, we're the #1 media platform worldwide for quantum technology. We also have our own proprietary data platform where we track all parameters of the quantum market. I'm also the founder of my own company, Universum Labs, which is focused on promoting education specifically related to quantum concepts. And I'm an advisor for Girls in Quantum, which is promoting education for girls worldwide.
Fantastic. I'm Garrison Buss, CTO and co-founder at QSecure. We provide quantum resilient encryption to protect against the quantum threat, like Sumi is introducing via applications of Zapata. Again, we can get more into that in a bit, but it's actually not quantum. It runs on classical infrastructure that protects against quantum attacks.
Okay, so now I'd like you to now imagine that you're in Davos. Okay, not hard to imagine. But now you've got, let's say, an investor, a corporate, somebody that you're speaking to, and they know a little bit of quantum, but they want you to go deeper and that things that only you would know. Who wants to take that first? You were smiling a lot, so sure. Yeah, I'm like, yeah, give it to me.
That's what I get for smiling, sure. Well, you know what? I think that I'll add a little bit of nuance to the quantum ecosystem, and then I'll give you a little bit of the kind of inside story. And so the nuance around the quantum ecosystem is the way we think about quantum is we think about the generalized quantum stack. We're in computing, so there has to be a stack. And the way that we think about the stack is there's a why, a what, and a how. And the why is the problem that you're trying to solve. So it could be drug discovery, factoring large numbers and blowing up the world of encryption, which they're not trying to blow it up. They're trying to fix it after somebody else blows it up. But in any case, there's the problem that you're trying to solve. That's the why. The what is the algorithm or the application you're using to solve that problem. So you may have an algorithm that might help with something like homogeneous catalysis that helps drug discovery. And then the how is the hardware execution, the actual putting this on hardware. And we're making a great deal of progress there. So I'd say kind of the inside track is we are making a great deal of progress on the hardware side, and we're seeing demonstrations of that. There's quantum advantage demonstrations that are saying, hey, we're now doing things that are impossible classically that we can do on a quantum computer. The issue is there's less progress in layers 1 and 2 above, where these demonstrations of progress are interesting, to academics, I guess, perhaps like Will, but they're less utility. And so right now, what we need to do is advance on layers 1 and layer 2. And layer 1 and layer 2, what we really need to have happen is greater collaboration. And I think that's really in the spirit of Davos, where what we need is greater collaboration with industry so that they can understand what's possible on quantum computers. And then we can apply these algorithms to a variety of different problem sets, which is something we do a great deal of at Zapata. So I'd say that's the inside track, is lots of progress on layer 3, a little bit less on layer 2, and even less on layer 1, but very exciting to be doing that work.
Maybe if I just, put up your hands if you know, let's say, a good amount on quantum. Okay, so maybe Will, can you give us a little primer for the audience?
Yeah, sure. So quantum computing is a new type of computing that uses quantum bits, or qubits as we call them, as the logic element. You can think of a qubit as the quantum analog to the transistor, with transistor being what we use in our conventional computers. And in a nutshell, the fundamental difference is that a transistor is completely classical. It's basically a faucet for current. I turn the current on and I turn it off, and I'm going to call it digital 1 and digital 0. It's a 1 or it's a 0, and that's it. But qubits, they're also two-state systems, 0 or 1, but the difference is because they're quantum mechanical, they can be in superpositions of 0 and 1 simultaneously.
What does a superposition mean?
A superposition means that you carry aspects of both of those simultaneously. So for example, if I wanted to do a computation and I was using qubits, I can explore zeros and ones at the same time. Now, it sounds like magic, but it's not. It's actually the way the world fundamentally works at the very small scale. And by small scale, I mean atoms, electrons, neutrons, things like that. But what we're trying to do is to bring that up to a large enough scale that we can build a computer, something that you can actually see with your eyes and take advantage of it. And that's what's ongoing right now. Because we're using quantum and we're using the superposition principle, things like quantum interference, quantum parallelism come into play, and it enables us to do with a quantum computer things that you just simply cannot do in a reasonable amount of time on a classical computer. In principle, you could, but it might take 10,000 years or 100,000 years. It's not that we don't know how to write those classical algorithms. It's just that they're completely inefficient, and on a quantum computer, they become efficient. Not every problem, but certain problems.
Well, and one of the things I actually tried to do some math for is the connections in Davos. But even if we just look at this room with this many people, how many things you do and how many potential connections you could have here and everything else, and every hour the answer could be different as well. That's a big, incredibly hard problem.
Yes.
But could, with an application layer on top, could we then somehow figure that out?
Let me ask the algorithm experts.
I'll just go really quick on that. So, at the end of the day, what you're talking about is an optimization problem. And so optimization problems exist in many varieties. This is a very interesting optimization problem that has not been framed before that I've heard. But there are many of them. There's things like supply chain optimization. There's the traveling salesman problem. Where do you put a hub for a manufacturing facility? How do you design a manufacturing facility? How do you design all the flights for a airline? How do you do portfolio optimization in finance? All of these are varieties of optimization problems, along with how do you optimize for the connections of the people in Davos and maximize the impact of us folks. But in any case, quantum computers are going to be very good at this. And we believe that this is an area that you can imagine with the types of problems that I'm proposing, supply chain optimization, logistics, financial optimization. There's a great deal of money and value creation that's going to come from this. So yes, quantum computers will be good at this.
Very good. So I've got a guy. And so today you're all using your phone. So I've got a guy and he's basically recorded every single piece of data in Davos yesterday. Okay, every piece of data is done. Now, obviously, it's really safe and it's protected right now, but is it? So if I do store now, can I decrypt later? But if you can explain what the issue is that we're talking about.
Yes, precisely. So
I have yesterday's data, it's on our.
Exactly. So as Sumi was describing, there's a unique feature actually, and Will was getting at this too, of quantum computers, that it just so happens that the encryption that we use to protect our data, and specifically data in transit today. So that means, for example, when I send a text message or send an email, or I have encrypted videos going to the cloud that are being synced, right? All of this represents data that is moving from one place to another. And the way that we secure that today relies upon a math problem that essentially is two prime numbers coming together that form a very, very large number, and they're factors of that large number. The benefit of this is that it's a function that is really, really easy to use to encrypt things. The challenge is that it just so happens that this problem is something that quantum computers exist in that space that Will was talking about. Difficult on a classical computer. Actually, it would take more time until the sun burns out than we could break even one of these keys. So in theory, they're very secure. But it just so happens that quantum computers can do this very, very rapidly. And this was discovered by a man named Peter Shor, actually also at MIT. And what he found was that a quantum computer could do this very efficiently. So efficiently such that it would be practical to break large numbers of these with a sufficiently scaled quantum computer. This all gets back to the point of, hey, I have data in transit today. What is the benefit of this thing called store now, decrypt later, or harvest now, decrypt later? And this idea essentially is something that is very well known, I would say, particularly in the intelligence communities, where they will harvest data that may not be immediately useful today. And you can, for example, record a encrypted session, which again, as I mentioned, right, would take more time until the sun burned out to be able to break into with classical computing. But if that data has a long shelf life, so imagine, right, for example, if you've been at your bank for more than 5 years, if you have, in the case of the US, a social security number or something similar, right, that data is still valuable 5, 10, 20 years from now. And so too, right, nation states have secrets and other things that they want to be able to keep safe for that period of time. And if someone else were to record that data today, and then, in 3, 5, 10 years, when a quantum computer comes online, they could decrypt that information and it would still have value to them, right? It's of interest now to keep it safe. And so what folks like we are doing is to help large enterprises and government transition to this new type of encryption. And maybe just to play off, what folks might want to know about this, I would say two things. I hinted at this at the very beginning, which is that this problem is actually a solved problem. There's no magic that needs to happen in order to protect our data today. NIST, the National Institute of Standards and Technology in the US, started a competition 10 years ago. So again, they had a lot of foresight on this to find algorithms that would be resistant to both classical attack and quantum attack. And over that time, they basically down-selected into a new standard, which is now FIPS 203. And that is something that can be used by anyone today. It's open source. And that can be used to protect data. So one thing is that it's a solved problem. It's just how do you implement? The other thing is, again, I just want to be super clear about this. You don't need quantum to fight quantum. So you have a quantum computer is the thing doing the attacking. But actually, to apply the resilient encryption, you only need classical computing.
And by the way, when you say it's a solved problem, I mean, like technology, yeah, solved problem. Does that mean that whatever, my private pictures that I stored a year ago, does that mean that they're protected forever? Or do I need to do something? Or does Apple need to do something? Because I hear the words, I don't understand what they mean in practice.
Yes.
So is all our old data going to be protected or not?
Yes. So interestingly, there's two types of encryption. One is asymmetric and the other one is symmetric. Symmetric is what protects data at rest. So basically, after the data has already been recorded, for example, on your iPhone, after you record the video and it's stored, that's encrypted with a symmetric key, and that's widely regarded as quantum resilient today. So you don't need to change that. The thing that does need to be upgraded is the data in transit. So what I'm saying, I guess, is that if the data is already local, right, either it's in the cloud and it stays in the cloud, or it's on your phone and it stays on your phone, that is actually fine. It's just when you go from your phone to retrieve it from the cloud, that's the piece that needs to be upgraded. And that's the piece that actually Apple implemented this. I don't know if they've done it for their cloud yet, but at least on iMessage, they implemented this, I think, almost a year ago. So all of your iMessages today, if you're texting those, are safe, and so too has Signal done the same.
iMessage.
iMessage, yes.
Yeah, right. Okay. But not WhatsApp or anything useful.
Signal has also, they have sparse post-quantum ratchet. That's a really very interesting for cryptographers, but probably not for most people. It's very secure. And WhatsApp, as far as I know, has not implemented PQC yet.
Will you have a...
Oh, I was just going to say that, we don't have quantum computers yet today at a scale that will decrypt today. And so this becomes a risk-benefit question, right? Do I think we'll have a quantum computer in 3 years at the scale that it could actually decrypt our data and we're insecure? No, I don't think so. 5 years? Probably not. 10 years? Now I'm becoming much less sure, right? And it's going to take time for us to implement these new so-called post-quantum crypto schemes that Garrison was talking about. And we need to start now because of this, harvest and store. We all have information that we want to maintain security over, business plans, bank information, social security numbers, whatever it is. And we're transiting that data all the time. And so even if we're storing it during the transit, this key, if somebody, an adversary, were to gain access to it, now or in the future, that information becomes available to them. So we really need to start switching over. It's going to take 5 to 10 years to do it.
Well, so, if we look at, right now, health records, hospital system, they're sent basically in the clear. They would just be visible in 10 years' time, maybe.
That's right.
So surely this is a case of gross negligence on behalf of board directors of having, right now, if a hospital system was today saying all of our data is in the clear, they would all go to jail. All of that data, though, is still going to be visible in 10 years' time. Surely there's a communication problem here. How the hell do we get people to understand that right now they're basically being gross negligent by not addressing this issue? Do you have any solutions?
I think that's a really great question. And I will say that two nuances that I think are really important, both Will and you touched on. So the first one being that you don't need a quantum computer to protect against a quantum computer. And I think this is where a lot of the communication goes awry, because we definitely vary on terms of how each of us communicate timelines. I think we're all pretty much agreed that we can fit within the 5 to 10 year timeline. Granted, we've been saying that for years, so that's up for debate too. And then the second piece is really that yes, your data is protected today, and yes, you might have 10 years before we have an issue, but the migration to PQC algorithms takes a lot of time. And especially if you look at these processes within government and healthcare, these are very slow-moving processes. It's very slow to implement new things as it is. And so this is definitely something that a lot of us in quantum are shouting quite passionately, hey, we need to make the transition. We really need to implement it. And the hope was that with NIST having the competition and NIST selecting the algorithms, that we would start to see a lot more movement. But we actually did, there was a survey that came out, I believe it was end of 2024, that found that 60% of leadership across these very important industries knew about the risk of quantum, but only roughly 2% of them had made any decisions to start the implementation process. So that's incredibly concerning.
Why is it so slow? I mean, is it technically slow? Is it somebody has to go around with a floppy disk into a server to what's up, right?
So I think there's two parts. So one, I think it's technically slow. And then the second part is, again, getting people to understand the urgency behind it and to prioritize it. So it might be one of those things where it gets to the chief of information, but it's probably down there on the priority list because they think, oh, I have 10 years, no problem. So it is very much a communication problem. I wholeheartedly agree. And we hope to build more urgency around it. We did dedicate this year as the year of quantum security for that reason. So hopefully we see something.
Of course, it also costs money, right? This is not going to be cheap to switch over. It sounds like it's all software, but it's not, unfortunately, all software. Many military systems have hardware that's embedded specifically so it can't be hacked in this way, but we have to replace that hardware now. So a lot of changes have to happen, and it's going to take time. It's going to take money. Question back there, too.
Can you add any comment about blockchain and how quantum is going to be blockchain?
Yeah, I mean, it's and people have said, okay, why have Bitcoin? Because Bitcoin's encrypted. As soon as quantum comes out, it's basically all worthless. What's up with that?
Well, I'll say it's not like flipping a switch, right? So as Will had mentioned, there's going to be increasingly powerful quantum computers, right? And so at different levels of compute, these quantum computers will be able to do and more advanced operations. And so there's segmentation between the different types of algorithms that Bitcoin uses to remain secure, right? So your wallet, right, with a public and private key are the first things that are among suspect. And, those should probably be migrated first. But then there's the hashing algorithms and so on that are, again, possibly quantum vulnerable, but a little bit further down the line. And so the idea is that if you have a quantum computer, of course, cryptocurrency is massively valuable, at least today, and that might represent a great first target, right? If you're going to break a single key, that would probably be, a Bitcoin wallet with many, many millions of dollars, and it would probably be a pretty good one. In fact, there's actually challenges where people have put money into a Bitcoin wallet to see, hey, if this basically, I'm never moving this money. If this money comes out, that means that somebody has a quantum computer. Although there are wallets with much more, and they would probably go after those first. But so I guess in short, just to say that it's not going to be like an all at once. And then the other piece is that you might not want to reveal yourself in that way, right? So if someone's funds come out of their wallet and the only explanation is a quantum attack, that is revealing that somebody has this ability. And it may not be something that they want to reveal, right? It could be, right, as soon as somebody knows, now, again, the pressure might be much more on to transition to new versions of the encryption that's going to prevent that, right? So it's kind of like a one and done sort of a deal. So if, again, like any type of code breaking, as soon as somebody knows that you've broken the code, that then kind of puts the impetus to try and transition to something else. So again, it's kind of a mixed bag, but just to say today, Bitcoin is quantum vulnerable. There are other versions of blockchain that are not necessarily vulnerable. And Solana has implemented PQC as well as, I think, Ripple maybe now has a fork. But it's definitely on the periphery, not in the mainstream. And this will be something that has to basically be adopted.
Yeah, but the wallet,
yes,
like you said first, the wallet is definitely, of all of it,
yes,
that's suspect.
yes.
So, I mean, I think maybe I'd like to take a step back to look at the technology, the actual quantum computing technology. Now, quantum technology has sort of three different areas. We've got a communications area, we have a sensing area, and we have the compute area. So it's not as though we're just saying a quantum computer is this. So right now, you have nanosensors and all kinds of stuff, but we're really focusing, I think, at the moment on quantum computing. what is state of the art? But if you can describe it, but I think fundamentally what's interesting for me is what should I be looking out for as key milestones that if this is solved, then we're in a different. It's just like ChatGPT type of thing. So so
What's the tipping point?
exactly?
Yeah. So, as you might imagine, we don't see quantum effects in our everyday lives. We're not in two places at once, right? And the reason for that is quantum is fragile, right? And any time a quantum system interacts with another system, this quantumness goes away. So these have to be highly isolated systems. And as we build them over the last 10 or 20 years, we've gone from, say, 1 qubit, think of it as 1 transistor, 2 qubits. We're now up to about 100 to 1,000 qubits. You might think, well, that doesn't sound like a very large number. If they were perfect qubits and there were never an error, that would be enough to actually do the things that we've talked about so far here. But they're not perfect. They're imperfect. And so one of the major challenges and the tipping point that we're talking about is called quantum error correction. It's a means by which we run protocols that fix the errors faster than they occur. You can think of the spinning saucer on a stick, and you're trying to keep that up in the air, and it easily falls off. But the better we are at controlling it, the longer it stays up in the air.
It does sound like organizing a Davos and unDavos summit.
Yes. Mark, you're familiar with
We
this.
have a quantum state, definitely.
Yeah. So I think that is the number one challenge, and the tipping point is happening right now. So, for example, fall of 24, Google made an announcement that they had demonstrated quantum error correction at a level that hadn't been previously shown. And to give an idea of what the challenge is, let me give an analogy that I find quite useful. Many of us have kids. I have a kid. He's 16 now, but he used to be 5 years old, and I would take him to the playground. And there are other kids on the playground, lots of them running around, some falling down, some laughing. Everybody's having a good time. Total chaos, right? If I add more kids to that playground, what do you think? Chaos goes up or down? Of course it goes up, right? They're kids, right? And I think, they're kindergartners. And 10 or 15 years ago, all of our qubits were kindergartners. They would fall down a lot, right? Okay, so what happens? In the intervening years, of course, they go to elementary school, and over time, they become more and more performant. And at some point, it actually makes sense that I'm going to take 2 or 3 of them, put them together, form a team on a project, and the team outperforms any of the individuals. That is called quantum error correction, right? Or we would just call it a team. We form a team of qubits. So what Google did is they formed a team that had 17 qubits, and then they formed a team that had 49 qubits, and then they formed a team that had 97 qubits. So the number of qubits is going up, the size of the team is getting larger, but what happened? The chaos went down, the error rate went down. And that we've known theoretically since the 1990s. In fact, St. Peter Shore helped us learn this. But it was the first time we'd actually experimentally demonstrated it. It was a major milestone. And in fact, all of the quantum stocks went up with that because we all know how important it is to see that. Now, we're not done, right? The improvement in error was a factor 2 each time we made the team larger and larger. We need to do more. Where do we need to get to? That's another question. What error rate are we looking for? Many of the applications that Sumit was talking about, we need to run 1 billion or 1 trillion operations. Okay. On a classical computer, no problem. We can run 1 trillion operations anytime. But on a quantum computer, our error rates today are about 1 in 10,000. That means we can run about 10,000 steps, and on average, we'll have 1 misstep. Okay, so we have a big gap. We have to get from 1 in 10,000 to 1 in 1 billion or 1 in 1 trillion. And how are we going to get there? Quantum error correction.
Well, and how much? I mean, if you look at AI, it's interesting having conversations on AI right now because the conversation very quickly turns over into energy and chips and other things. So I hear what you're saying, that it's all about error connection, but once that one is fixed, what is the next bottleneck? What's going to come up next? Or are there things on the software side, different levels of the stack where you say, yeah, you're right on this level of the stack, but we have this whole bunch of issues up here. Maybe Sumit?
Yeah, sure.
So this kind of gets back to where I was initially, which is, at the end of the day, actually Google put out a paper, and it was actually in December of 2025, so just a month ago, and they called it the Grand Challenge of Quantum Applications. And in that paper, they noted that the gap that exists right now is that we have a collective action problem. We have a lot of the full stack providers who are dominating a lot of the landscape. They're focusing on the hardware and they're not focusing as much on the application side. And so I think the bottleneck, to your point, is the focus on the application side. And to be really specific about what that means maturing applications such that we actually get them to the point where they're going to provide quantum advantage when these systems come online. So for example, where we are right now is we have a few applications. So things like Shor's algorithm, quantum chemistry is a space that we're fairly advanced. Quantum simulation, the simulation of other quantum mechanical effects and things like condensed matter physics. That's things like superconductors and batteries. Obviously, these are really, really interesting problems because if we solve the problem of superconductors, then we can solve the problem of nuclear fusion, for example. And quantum chemistry, if we can solve the problem of quantum chemistry, then we can solve the problem of drug discovery, industrial chemicals, petrochemicals, agricultural chemicals, really, really large problems. So we've made progress on some of these domains, but there's other domains where we're more nascent and we have to make the connections between the use cases at the top and the algorithms that are maturing in that kind of middle layer. And those domains that are more nascent, where the bottleneck exists, are things like optimization. We talked about the optimization problem and how it might apply to supply chains and manufacturing and logistics. Simulation, there's defense simulations, there's finance simulations, there's simulations of aerodynamics and fluid dynamics. That's an area that we need further progress on to connect the use case layer to the application layer. And then there's machine learning, where some companies are focusing on applying quantum to machine learning. And obviously that would unlock a lot of potential in advancements in AI. So I'd say that the bottleneck is indeed on the software side. And as we get more collaboration with industry and get folks to actually build their quantum muscle, which I think is the topic of the next panel anyway, as that muscle gets built, we actually cross some of those hurdles and unlock that bottleneck to create more progress in the future.
Yeah, I would also say one of the challenges is scaling. And we can demonstrate 97 qubits, for example, or 100 qubits, 150 qubits. And that is state of the art. And these are fully functional quantum computers, but it's the computer that I remember using in the late 70s or early 80s, or maybe even before that. Timex Sinclair, if anybody remembers that, not very powerful. You could do a few things on it. You knew that it worked. It had an OS. It had an operating system. It had, you could do things, but nothing that you would really find to be useful yet. So we need to scale them up. And there are different technologies, right? Some are based on elements, natural atoms that we have in our universe, and those are trapped ions, neutral atoms, for example. Others are manufactured qubits, like superconducting qubits, basically an electrical circuit that we manufacture. What we're seeing is that the superconducting qubits, for example, we can run a lot of operations. They're pretty high quality, but the challenge is in scaling to large size. The natural elements, we can trap thousands and thousands of atoms, but we can't run them very long. And so there's this dichotomy that it's occurring. One of these technologies, we can get lots of qubits, but they're not very performant for very long. The other one is that we can see how to run lots of operations, and the challenge is actually getting a lot of them. So this scaling effect, I would say, is a key challenge.
But it feels as though there's a thinking problem here. So now we're using AIs. I was doing machine learning stuff, 10 years ago, 5 years ago. But then if we look at the transformers that Google came out with pretty much now has given us this whole generative AI world, but it was a change in thinking. So are there these new, it looks as though this quantum problem is fundamentally, can humans think? But then maybe we should bring up AI. Is AI going to help us solve some of these technical problems?
Yes.
That's all I was looking for. Okay, good.
No, it's
is there like a prompt that we can type, or?
There's actually an interesting quote, and I'll if you guys had some comments, I'll pass it over to you guys. There's an interesting quote because what you bring up is a very solid point. And so there was a physicist by the name of von Neumann who was a very prominent physicist around the advent of classical computers. And his, at the time he was thinking about what classical computers would be used for. And at that time, we're talking about probably the 50s and 60s. And classical computers were used mostly for scientific results. And what he said at that time is, he said the most important applications for these digital computers are likely to be the ones that are very far off from what is predictable today, because it's going to be problems that are outside of the realm of what is currently feasible. So we do have, an imagination problem, a thinking problem in the direction you're going in. And a lot of what we're doing at Zapata actually is bringing AI to the process of application development so that we can accelerate that process and actually use AI to augment our imagination and augment our ability to take these applications and connect them to the algorithms, and then ultimately be there when we scale, in the spirit of what Will was talking about.
Yeah, I would say that just quickly, there are two ways that I look at this. One is AI for quantum, and the second is quantum AI, quantum for AI. We're already using AI to make our quantum computers better. Classical AI, and we're doing it, my students do it. Just imagine having to tune up 97 qubits. It takes a long, long time. Of course, we don't do that by hand anymore. We have AI agents that are doing it on our behalf. So that's real, and that's happening right now. What will happen next, as Sumit just said, is using a quantum computer to do better AI. And how to do that, that's a topic of research. It's ongoing right now.
So I wanted to kind of briefly come back to the point that we were making, what is the next challenge? And you mentioned the need for more industry collaboration. And so I think this is really important, especially as I'm considering the room. I know that there are some of you out there who are in the industry, I recognize you, and then some of you are not. And so if we're here at this conference speaking to end users, then I think it's really important for end users to understand that in order for us to get quantum computers to where we need them to be, yes, we need the hardware, but we also need the software. So quantum algorithms are lagging behind quite a bit. And it's really, really important for hardware providers to get out into the field and to partner with industry partners so that we could start doing more industry pilots and see what happens using real life scenarios on real world test data. That's very, very important. And at the Quantum Insider, we actually did a market report on this recently, and we found that by 2030, if end users were to regularly employ quantum computers, even at the early fault tolerant stage, there's the potential for 800 billion in value created for the end users specifically, not necessarily for the hardware providers. But that's a very, very large amount of value. And if we look at the place where quantum can be used, such as in pharma, insurance, etc., these are trillion-dollar industries, and they stand to be optimized by quantum computers once we have the technology in place. So yes, we have a scaling problem, but we also have a problem with actually going out and testing what we do have.
Very good. And now we have time to open it up to the you people here. So please put up your hand if you have a question. We have a mic here. If we do one here and then one here. So very good. Lady here first.
Thank you. What is the big difference between classical AI and quantum AI?
Yeah, classical AI is, of course, what we're actually using today when we say AI, whether it's ChatGPT, Gemini, Microsoft version. And we can use that AI to design or calibrate or implement our quantum systems and make them more performant. That's classical AI for quantum computing. Quantum AI is TBD, to be determined. But the concept is that I'm actually running the AI, whatever it is, or the training on my quantum computer, right? That's the difference. That would be quantum AI. There's one offshoot of this, which is somewhere in the middle, which is that if I want my classical AI algorithms to say, help me design a better drug, it would be a good idea if I trained them on quantum data, because they're currently trained on classical data that's available, say, online, and it's all classical. But I'm asking it to do something to simulate or to imagine a better, say, pharmaceutical drug, which obviously has quantum effects involved in the chemistry. So we can use a quantum computer to generate quantum data and then use that data to train a classical AI on a classical computer so that it's better at doing that task. That's somewhere in the middle. The difference is in how the processing is done. The outcome, in some sense, is the same. You're going to get one answer. And the difference is, how do I obtain that answer? And on a conventional computer, we use Boolean logic, it turns out, zeros and ones. And we run an algorithm, and at the end, we take a series of steps, and we go from one point to the other point. Okay, that's the answer. In a quantum computer, due to quantum superposition and quantum interference, at a quantum version of parallelism, we can explore essentially all possible answers at the same time. You can ask a question. There's one of many possible answers it could be. Quantum computers can explore all of them at the same time. But what a quantum algorithm does is it suppresses all the wrong answers basically to zero, and it enhances the one that is correct to one, so that when we make a measurement, we get the right answer at the end. So we start with an equal weighting of all possible answers, and if we made a measurement, we would randomly get any one of them, because we can only get one answer in the end. We're classical beings. But the quantum algorithm's job is to make sure that the right answer is enhanced in likelihood, and the wrong answers are all suppressed. So we make a measurement, we get the right answer.
And by the way, if it's okay, I'm going to dumb it down even more with a simple example. So right now, okay. Now, you got to spread that. Okay. What I just did is that I told him a number. Now, in classical computing, goes one, maybe to that one, and that one. So it would take quite a long time for this number to spread one by one by one by one. Or I could say 2,790, and you will get it all at exactly the same time. It's almost the difference between doing one-on-one versus broadcast. Now, it's more complicated than that, but that at least should give you an idea of scale. Imagine showing something with 10 billion people at the same time instead of one. But anyway, I'm dumbed down. I think we have time for one. We have time for one question, Jonathan.
Yeah.
Yeah. Okay.
We can do two more questions.
Two more questions. Okay. One here, and then there'll be one final one at the back. Yeah. Thanks.
So, well, I'm contemplating between a practical and a devil's advocate question. So, first, I'm very excited about quantum. My name is Eyal. I'm CEO of Cognifiber. We do photonic computing, but I want to go to the astrophysics. We know that in quantum, the same photon that started from the Big Bang and hit us now actually has no time. So for it, there's zero time, and he crossed the entire universe. So my question is, when we do quantum computing, can we send a signal across the universe in zero time?
Yeah, so the idea here is that if you entangle two particles, say two photons, particles of light, and I keep one, and I give one to you, and then you go really far away, light years away, because they're quantum mechanically entangled, when I make a measurement, it will impact the photon that Eyal has, right? And it seems like that traveled at the speed of light, or it exceeded the speed of light, because it was instantaneous. Okay. But the conundrum is undone by the fact that I had to give you that photon, and that was done subluminally. And you went somewhere else, and you're clearly not going faster than the speed of light. I know you can run fast, but not that fast, right? And so we didn't actually communicate anything useful faster than the speed of light, even though the rules of quantum mechanics, and this is the way the world works, means that when I do make a measurement, we have an intimate quantum mechanical connection that my measurement will impact what you will measure, even if you're very, very far away. But we didn't exceed the speed of light, right, in the whole process.
Can I idiot proof again? Idiot proof again, okay? So, okay. You and me? No, you're okay. So right now, I'm going to lift up my hand. You lift up your hand. Good. And we're down. Okay, we're now entangled. Okay. Now we could entangle more. Okay, everybody? Good. Now let's imagine that I go off to Berlin and I put my hand up, and all of a sudden, all of you match. Again? Okay, was a demonstration of entanglement.
Yes.
From Will, this is an extremely good answer.
All right, we have time for one more question.
Hi, I'm Muna Edeveen. Amazing panel. Thank you so much. That was really clear. Just a point on what is it, Chiara? Sorry, I can't really read that from here. Chiara, amazing point. And I just released a framework for post-quantum transition. So if anybody in the audience is equally worried about this and would like to, spread the word as to how organizations can transition, go to muna.net, Mike October November Alpha.net, and the framework is on there for free. Thank you, guys. Amazing work.
So with that, I'd like a huge round of applause for us, for our incredible panel. I've learned a lot, so thank you ever so much. And please stay, because the next panel is coming up. We're now doing the switch from technology into the use cases, the really cool stuff. So with that, thank you very much.